Good morning. My topic is Raman spectra. General introduction. It is a special type of spectroscopy which deals not with the absorption of electronic radii but deals with the scattering of light by the molecules. It is observed that when a substance which may be gaseous, liquid or even solid is irradiated with monochromatic light of definite frequency mu, a small fraction of light is scattered. Rayleigh found that if the scattered light is observed at right angle to the direction of the incident light, the scattered light is found to have the same frequency as that of the incident light. This type of scattering is called Rayleigh scattering. Professor C.V. Raman of Kolkata University, however, observed in 1928 that when a substance is irradiated with monochromatic light of definite frequency mu, the light scattered at the right angle to the incident light contain light lines not only of the incident frequency but also at lower frequency and sometimes of higher frequency as well. These lines with lower frequency are called Stokes lines, whereas the lines with higher frequency are called anti-Stokes lines. Raman further observed that the difference between the frequency of incident light and that of a particular scattered light was constant depending only upon the nature of the substance being irradiated and was completely independent of the frequency of the incident light. If mu I is the frequency of incident light and mu s that of a particular scattered light, the difference delta mu is equals to mu I minus mu s is called Raman's frequency or Raman shift. Thus, the Raman frequencies observed for a particular substance are characteristics of that substance. The various observations thus made by the Raman constituents what is called Raman effect, and the spectra observed is called Raman spectra. Thus, in a simple way, Raman spectra may be observed as shown in figure 3.29. Explanation for the observing Rayleigh lines and Raman lines. When the incident photon hits the molecules, this collision may be elastic or inelastic. Elastic collision means that the colliding particles will return with the same energy, thus the scattered photon has the same frequency as that of the incident photon. This explains Rayling's scattering and Rayling's lines. However, if the collision is inelastic, still the law of conservation of energy will hold good, that is total energy before collision and after collision must remain the same. Thus, some energy may be transferred from incident photon to the molecule so that the scattered photon has lower energy and has lower frequency than that of the incident photon. This explains the occurrence of Stokes line. Alternatively, some energy may be transferred from the incident photon to the molecule so that the scattered photon has higher energy and hence higher frequency than that of incident light. This explains the occurrence of anti-Stokes lines. This explanation may be further elaborated as when the photons strike the molecules, the energy is observed by the molecule and is get excited to some higher energy level. Now, if it returns to the original level, it will emit the same energy as absorbed, and thus we have Rayleigh scattering. However, in the most of the cases, the excited molecule does not return to the original level. It may return to a level higher than the original level, thereby emitting less energy than absorbed. This explains the occurrence of Stokes line. Thus, a part of energy of the incident photon remain absorbed by the molecule. Alternatively, the excited molecule may return to the level lower than the original level. Thus, more energy is emitted than absorbed. This explains the occurrence of anti-Stokes lines. In this case, the molecule has a less energy than before. The different cases may be represented diagrammatically as shown in figure 3.30. Levels has been shown equally spaced just for the sake of the convenience. Polarizability of the molecules and Raman spectra. The Raman effect arises on the account of polarization of the scattering molecule that is caused by the electric vector of electromagnetic radiation. The induced dipole moment mu depends upon the strength of the electric field E and nature of the molecules. We write dipole moment is equals to alpha I, where the quantity alpha depends upon the nature of the molecule and is called polarizability of the molecule. Thus, the polarizability is the ratio of the induced dipole moment to the strength of the electric field. In case of atoms or spherical symmetrical molecules, spherical rotors such as CH4, SF6, etc., Same polarizability is induced whatever be the direction of the applied electric field. They are said to be tropically polarizable. Such molecules are said to be isotropic molecules. In case of all diatomic molecules, homonuclear or heteronuclear non-spherical molecules, non-spherical rotors, the polarizability depends upon the direction of the electric field. For example, in case of H2 molecule, the distortion produced is more when the electric field is applied parallel to the bond than when it is applied perpendicular to it, and we write alpha parallel greater than the alpha perpendicular. Such molecules are therefore said to be anisotropically polarizable. Type of molecule showing rotational Raman spectra. A molecule is scattered light because it is polarizable. Hence, the gross selection rule for a molecule to give a rotational Raman spectra is said that the polarizability of the molecule must be anisotropic. That is, the polarizability of the molecule must depend upon the orientation of the molecule with respect to the direction of the electric field. Hence, all diatomic molecules, Riemann molecules, and non-spherical molecules give Raman spectra. That is, they are rotationally Raman active. On the other hand, spherically symmetric molecules such as CH4, SF6, etc. do not give rotational Raman spectrum. That is, they are rotationally Raman inactive. These molecules are also rotationally microwave inactive. In fact, this is one of the reasons for the importance of rotational Raman spectroscopy over infrared spectroscopy, because the latter requires that the molecule must have a permanent dipole moment, whereas the former only requires the polarizability of the molecule must change during vibration. Explanation of Raman effect in terms of polarizability. The polarizability alpha of the molecule that is rotating or vibrating is not constant but varies with the frequency of vibration or rotation. It is the sum of two parts, namely equilibrium polarizability alpha naught, that is the polarizability when the atoms of the molecules are in equilibrium position. Second, sum of the polarizability of the molecules due to the various rotational and vibrational motions. Each terms depend upon the frequency of rotation or vibration. Thus alpha is equals to alpha naught plus summation delta alpha n by delta r into Rn cos 2 pi mu n t, where alpha n is the polarizability associated with the nth rotational or vibration mode and Rn is the maximum displacement of the atom involved. Further, the electric vector of the electromagnetic radiation varies with the time in a sinusoidal manner as E is equal to E naught cos 2 pi mu naught t. Substituting the value of alpha and E naught from equation 2nd and 3rd in the equation 1st, we get magnetic moment equals dipole moment equals to E naught alpha naught cos 2 pi mu naught t plus summation alpha delta alpha n upon delta r into Rn cos 2 pi mu n t cos 2 pi mu naught t. Now dipole moment is equals to E naught alpha naught cos 2 pi mu naught t plus half E naught summation delta alpha n upon delta r into Rn cos 2 pi mu n minus mu n t plus cos 2 pi mu naught plus mu n into t. This expression consists of three terms. The first term has the frequency of incident radiation and represents Rayleigh scattering. The second term contains mu naught minus mu n and represents stroke lines, and whereas the third term contains mu naught plus mu n and represents the anti-stroke lines. Quantum theory of pure rotation spectra of diatomic molecule. The selection rule for the pure rotational Raman spectra of a diatomic molecule are delta J is equals to 0 plus minus 2. The selection rule for delta J is equal to 0 correspond to the Rayleigh scattering, whereas the selection rule delta J is equal to plus minus 2 gives rise to the Raman lines as explained below. We note that the energy of the rotational line levels in terms of wave number with quantum number J is given by mu bar is equal to Bj into J plus 1. When a transition takes place from a lower rotation level with the quantum number J to a higher rotational level with quantum J dash, the energy observed in terms of wave number will be del V bar equals to Bj dash into J dash plus 1 minus Bj into J plus 1. For the selection rule, delta J is equal to plus 2, that is j dash minus j is equal to 2 and j dash is equal to j plus 2, we get delta v mu bar equals to b into j plus 2 into j plus 3 minus bj into j plus 1 is equals to b4j plus 6, where j is equal to 0, 1, 2, 3 and so on. Again for the selection rule, delta j is equals to minus 2, that is delta j dash minus j is equal to minus 2 or j dash is equals to j dash plus 2, we get delta v bar equals to bj dash into j dash plus 1 minus bj dash plus 2 j dash plus 3 is equals to minus b into 4 j dash plus 6, where j dash is equals to 0, 1, 2, 3 and so on. Combining the result of equation 3 and 4, the wave numbers of the line obtained in the Raman spectra will be given by mu bar is equals to mu I bar plus minus delta mu bar, or mu bar is equal to mu I bar plus minus b into 4j plus 6, where j is equal to 0, 1, 2, 3 and so on. Here mu I bar is represent the wave number of the railing line, plus sign gives lines with higher wave number called anti-stoke lines, and the minus sign gives lines with lower wave number called stoke lines. From the equation 5, it may be seen that for j is equal to 0 and mu bar is equals to mu I bar plus minus 6b, that is the first stoke line and anti-stoke lines, will be at a separation 6b from the railing line. Further, putting j is equal to 1, 2, 3 and so on, the separation between any two adjacent stoke lines or anti-stoke lines will be 4b. Thus, the pure rotation Raman spectra expected for a diatomic molecule may be represented as shown in figure 3.32. Intensities of a line of the pure rotation Raman spectra. As explained earlier, the intensity of line depends upon the population of initial level from where the molecule are excited or de-excited to final level. Since the population of rotational energy level is as shown in figure 3.20, therefore the intensity of the Stokes and anti-Stokes line vary in a similar manner. Application of pure rotational Raman spectra. From the pure rotational Raman spectra, noting the separation between the lines, the value of B can be obtained, from which the moment of inertia and the bond length of the diatomic molecule can be calculated as explained earlier. Quantum theory of rotational vibration Raman spectra of a diatomic molecule. For large number of molecules, the lines obtained due to rotational transition are so weak that they are beyond resolution. Hence, we have pure vibration Raman spectra, for which the selection rules are same as for pure vibration spectra discussed earlier. However, in the case of the diatomic gaseous molecule, the resolution of rotational fine spectra is sufficient and can be studied. Thus, the diatomic gaseous molecule give rotational vibration Raman spectra, which can be explained as follows. The selection rule for the transition are delta mu is equal to plus minus 1, delta j is equal to 0 plus minus 2. However, at the room temperature, as most of the molecules are in lowest vibration level, mu equals to 0. Therefore, the significant vibration transition is from mu equals to 0 to mu equals to 1, called fundamental vibration transition. Restricted ourselves to this vibration transition, only the result obtained are as follow. For delta j equals to 0, delta mu is equal to omega e into 1 minus 2 xc, called Q branch. For delta j is equal to plus 2, delta mu bar equals to omega e into 1 minus 2 xc plus b into 4j plus 6, called S branch. For delta j equals to minus 2, delta mu bar equals to omega e into 1 minus 2 xc minus b into 4j dash plus 6, called Q branch. Representing the value of Q, S and O branch by delta V bar Q, delta V bar S and delta V mu bar O respectively, and the wave number of the exciting radiation by mu bar I, the wave number of the Stokes lines will be as follow. Mu bar Q equals to mu bar I minus delta mu bar Q. Mu bar S equals to mu bar I minus delta mu S mu bar O equals to delta mu bar I minus delta mu bar O. We have considered the case of the delta mu equals to plus 1, which represents Stokes line. The anti-Stokes lines are those for which delta mu equals to minus 1. They are usually weak because very few molecules are in the excited vibration state initially. The rotational transition accompanying the vibration transition from mu equals to 0 to mu equals to 1 and the rotation vibration Raman spectra obtained may be represented as shown in figure 3.32. Advantages of Raman spectroscopy over infrared spectroscopy. Raman spectroscopy has a number of advantages over infrared spectroscopy as briefly explained below. Since Raman's frequency are independent of the frequency of the incident radiation, by suitable adjusting the frequency of the incident radiation, Raman spectra can be obtained in the visual spectrum ranges where they can be easily observed rather than the more difficult infrared range. Raman spectra can be obtained even for a molecule such as O2, N2, Cl2, etc., which has no permanent dipole moment. Such a study has not been possible by infrared spectroscopy. Raman spectra can be obtained not only for gases but even for liquid and solids, whereas infrared spectra for liquid and solids are quite diffuse. Because of the ease with which the Raman spectra can be studied, the molecular structure of a large number of compounds has been determined by Raman spectroscopy. However, infrared methods still continue to remain popular. Experimental arrangement for Raman spectra. The experimental arrangement for the observing Raman spectra is shown in figure 3.33. बस रहे हो क्या रहे? The fraction of the light scattered is so low that normally very weak Raman lines are observed. Hence, to detect these lines, it is necessary to use a powerful source of incident light. Earlier, mercury vapor lamp were used, which give an intense monochromatic radiation of wavelength 4358 angstrom. However, with the development of lasers, which are very powerful sources of monochromatic radiation, Raman spectroscopy has been greatly revolutionized. Thank you.